Okay, hi everybody. Welcome to the first flipped lesson for Year 11 Physics on vectors and scalars. Our learning intention for this particular lesson is to understand the difference between vectors and scalars and to be able to add two vectors together using the head to tail method. So let's get started. Just a quick recap from what we covered in class. Scalars are quantities that are fully described by a magnitude or numerical value only. Vectors, on the other hand, are quantities that are fully described by a magnitude and a direction. Both scalars and vectors describe physical quantities that can be measured. And some examples of scalars are distance, speed, energy, mass, temperature. Some vectors are displacement, velocity, acceleration, force. There are a whole host of others, things like magnetic field strength or electric field strength or drag or friction. There's a whole bunch of them. Okay, addition of vectors. When you're adding scalars, it's pretty straightforward. All you need to do, because they only have magnitude, all you really need to do is add the numbers together. There's no direction you need to take into account. Vectors, on the other hand, slightly more complicated. You have to take that direction into account, otherwise you'll get the wrong answer. To add two or more vectors, what you need to do is to line them up head to tail. You need to draw the resultant vector, or the answer, from where you started to where you finished. You need to find the magnitude of that resultant using arithmetic or Pythagoras' theorem. And you need to find the direction of that resultant vector using some trig and leave your answer as a true bearing. Let's have a look at some examples. Nice simple one to start with. Add these two vectors. They're both force vectors. One's 5 newtons, one's 3. All you need to do, as we said before, is line them up head to tail, so that you can see the 5 Newton vector. There is the head of that one, the tail of the 3 Newton vector, and draw the resultant from where you started from to where you ended up. And our answer is 8 newtons. Slightly harder one. Again, 5 newtons plus 3 newtons, this time 3 newtons in the opposite direction. Follow the same principles. Line them up head to tail and draw the resultant or the answer from where you started to where you finished up. Where you started to where you finished up. And you should end up with a resultant that looks something like that. The answer being 2 newtons. Okay. Again, slightly harder one. This time, the 3 Newton vector is north, the 5 Newton vector is east. Line them up just like we did before, head to tail. Draw the resultant from where you started to where you finished, like that. Pop in the angle theta. And now we need to find the resultant using Pythagoras and find the angle theta using some trig. To find the resultant, r squared equals 3 squared plus 5 squared, a squared plus b squared equals c squared. We end up with a resultant of 5.8 newtons. Theta, we're going to use sine, which is the opposite over the hypotenuse, the opposite being 3 newtons, the hypotenuse being the resultant of 5.8, gives us a value of theta, 31.3. Now that's not a true bearing. We need to find the true bearing. And the best way to do that is to imagine a compass. Straight up is due north, east, south, and west, and each quadrant is 90 degrees. As we move clockwise around the compass, we keep adding 90 degrees, or we don't need to in this instance. If that's theta, then the angle that we're actually looking for is 90 minus theta. So our answer is 58.7 degrees true. So down here you can see the resultant, the full answer, 5.8 newtons, 58.7 degrees true. Okay, So, reading the question, we know that it's obviously a vector question. So we've got a couple of vectors which we need to put in. Let's start with the swimmer's vector. Now the swimmer is swimming at 4 meters per second due north. So let's pop that vector in. There's the swimmer's vector. We'll pop that value in at 4 meters per second. Oops. And the current in the river is running at 5 meters per second due west. So let's pop that vector in there. And we'll label that at 5 meters per second due west. And our resultant, therefore, is going to be where we started to where we ended. So we'll draw a vector in there. And there is our resultant. Now I'll just label that to avoid any confusion. And we can start using Pythagoras now to solve for the magnitude of r, the magnitude of the resultant vector. So Pythagoras tells us that r squared is equal to 4 squared plus 5 squared, 16 plus 25, which is equal to 41. Therefore, r is equal to the square root of 41, which gives us a value of 6.4 meters per second. Now, using a little bit of trigonometry, we can solve for the value of theta, find the angle that vector is making, that resultant vector is making, and that's that angle in there. So if we use sine, so the sine of theta is equal to the opposite, is 5, over the hypotenuse, which is 6.4. 0.78. If we pop that number in our calculator and shift sine, or sine to the power of -1, that number, we should end up with theta is equal to 51.3 degrees. Now that is not a true bearing. If you look at the previous examples, we need to imagine that there's a compass here, and we need to measure the angle that goes all the way around there if we're going clockwise around the compass. So that's effectively 360 degrees minus theta. So the true bearing is going to be 360 minus theta, which is 360 minus 51.3, and that gives us a value of 308.7 degrees true. So our final answer is going to be 6.4 meters per second, and the direction of that final vector is 308.7 degrees true. Please get in a habit of circling your answer just to make it easier to see. Okay. Okay, well, I hope that's cleared that head to tail method for addition of vectors, the success criteria. Now you need to look back and think, can you explain the difference between a scalar and a vector? Can you add two vectors using the head to tail method? If you can do both of those things, I would like you to answer the questions that have been posted to Canvas. Once you've done those, we'll go through them next week in class, so don't worry if you're struggling. Okay, thanks for watching. Time to get to work.